Hello, in this video we'll take a look at what semantic image segmentation is using the DeepLab model in TensorFlow.js. So what is it? What is semantic image segmentation? It's nothing but a process of segmenting an image into multiple segments by labeling each pixel of that image and associating it to an object class. So each pixel is associated to an object class. That's basically image segmentation. Essentially, we are identifying all the objects that are present in an image and localizing them and marking the exact location boundary for each of those objects. This addresses one of the main challenges in computer vision, that is to to understand the image at a high level, like the way humans do. Basically, we understand by looking at an image what an image is. Let's say if an image contains two people sitting on a beach, then we are able to say that people sitting on a beach. So that's understanding an image at high level. Similarly, for a computer to understand an image at a high level, it needs to first recognize all the objects that are present, the background, the foreground, all the various objects that are present in the image, and this process helps with it by segmenting each pixel to a particular object class. So in that way, the computer is able to understand what the image comprises of. So that's semantic image segmentation. From an use case perspective or an application where this could be utilized, there's lots and lots of usage to it. The first one, as I described in the previous slide, image labeling, to put a title or basically describe an image, to put words for an image. This process could be used. Image labeling is one of them. The second one, human body segmentation. This is basically a subset of what semantic image segmentation is, in which we basically try to identify the exact location of a human body. First, we identify the overall boundary of the human body, and within the human body, we go into it and identify the location of the face, hands, legs, everything. Each and every part of the human body could be segmented. That's one. That is one example. The other one is medical imaging, wherein if you take an organ or a bone, such any part of the body, if you this process basically can segment each and every detail present in that particular medical image. Thereby, if there is something out of the ordinary, then it could pinpoint that particular spot, and it would enable the doctor to better diagnose what the problem is. The next one is obvious one, self-driving cars. In self-driving cars, it's essential for the system to understand what its surrounding is, where are the trees, where is the road markings, if there are pedestrians on the road, is there a signal there, other cars, buses, whatever it is. It has to get a holistic picture of its surroundings. So image segmentation could be utilized for that. The next one is manipulating the image, wherein if you get an image, you can point an object and then remove that object completely from the image. I think Google Photos has that functionality, and even some applications like Zoom or Teams, they are able to remove the complex background and replace it with a different background, keeping the image of the person in the foreground. So all that is done basically through this image segmentation process only. Moving on, let's take a look at the DeepLab model itself, which is utilized for performing this image segmentation. So it's a state-of-the-art model to perform image segmentation. In TensorFlow.js, this model is readily available for us to use as part of its pre-trained models suite. If you go to the GitHub repository of the TensorFlow.js pre-trained models, you'll find this model and the usage instructions there. The next one is the DeepLab model is packaged with three pre-trained weights. Each of those pre-trained weights correspond to a particular data set on which it was trained on, specifically Pascal, Cityscapes, and AD20K data sets. If you want to understand what these data sets are, maybe we can refer to this file. In this file, it basically tells us what are the different objects each of these models identify. What are the different objects that each of these models identify? For example, if you take Pascal, it is able to identify a background, aeroplane, bicycle. For cityscapes, it's basically identifying objects that you would basically see in a urban area. And AD20K is more, it comprises of more objects that it can identify. So these are the different objects that each of these models can identify. Now, moving on to the technical steps on how to install the model before using it. So there are two ways. One, if you're using a normal HTML JavaScript setup, then you can include those scripts using the script tag. The main one is the DeepLab.js, and these are all the dependencies that this model requires for us to have it available, so that it could use in the background. Or if you're using npm or yarn, then first install all these packages, and so that it becomes a part of the package.json. And then for using that particular model, use either of these statements. You import from that model, or you can use the require syntax. Basically what it does is it makes this variable available on which the model itself would be loaded, which would be basically referencing the model, using which we can invoke all the methods that we need. Moving on, to load the model, we call the DeepLab.load. As I said, the DeepLab is basically, this variable is available. If you are loading it using the script tags, then automatically this variable is available. Or if you're using import, whatever variable you gave for the import, that variable would be used. Or if you use the require syntax, whatever variable you assigned that syntax to would be available. So usually we assign it to the DeepLab variable. So we load the model by invoking the load function. Load function returns a promise. So we have this await in front of it, so that we are able to wait for the promise to be resolved, and we get the model assigned to the model variable. It takes two parameters as input. One is the base and the quantization bytes. What is base? Base basically refers to one of the three pre-trained models. So we need to specify the model name here. Pascal will load the model with the pre-trained weight of Pascal dataset. Cityscapes would do the cityscapes pre-trained weight of the cityscapes dataset, and same for AD20K. So that is base is nothing but the model name. Quantization bytes. This basically, before we look at the options available for quantization by bytes, let's take a look at what quantization itself is. Basically, it's a process that reduces the model's size so that it improves performance on CPU constrained environments like the browser, or mobile environments where the CPU is constrained there. It's not available in abundance. So in this process, they basically compress the model size to improve the CPU performance or the hardware performance. Obviously, there is a little compromise on the model's accuracy, but not significantly. So the quantization bytes parameter can take three options, 1, 2, or 4. Basically, it refers to how the weights are basically compressed. In the case of if you provide 1, the model basically it compresses the all the integer and float values to 1 byte. If you give it to 2, it compresses it to 2 bytes. So basically, 1 is lesser than 2, meaning 2 is better from a model performance perspective. And if you use 4, then you overall disable the quantization. So it's without quantization. So you would take a hit on the latency and the performance. Moving on, to predict, we use the model.segment. That method is used to that method is invoked for us to predict the segments on an image. You pass an image to it, and then it again returns a promise. So you call await on top of it, and then when you get back the prediction object. Now let's take a look at what the prediction object comprises of. This is a sample prediction object. Basically, it comprises of 4 attributes: legend, height, width, and the segmentation map. The legend is nothing but it basically contains all the different segments that was identified, or all the object classes that was identified on this image using the model that we loaded. So it gives so all the objects, or all the segments are associated with a particular color code. That's a predefined color code that the model has. So if the color code is 0, then it refers to the background. If it's the 192, 128, 128, it refers to the person. So those 3 values are nothing but the RGB color codes. Now in this specific case, it has identified 3 object classes: background, person, and motorbike, and it has assigned 3 different color codes for each of them. Now next is the height and width. This refers to the output image, whatever output image, segmented image that the model provides as output. What's the width and height of the image output. The final one is a segmentation map. This is the key one. Basically, it provides pixel wise color information for the image, for the entire image. So each pixel has 4 values associated with it. So there's 0, 1, 2, 3 is associated with 1 pixel, 4, 5, 6, 7 is associated with another pixel. The first 3 values are always RGB color codes. The last one is the alpha. Alpha basically tells whether the pixel needs to be visible or transparent. In this specific instance, because we want the entire image to be segmented to one or the other object class, it would always be set to 255. We want that particular segment to be visible, that segment's color to be visible. So it will always be set to 255, the alpha value. The other 3 would have the RGB color codes mapping to one of these objects. That's what it would be. So in this case, if you see, it has got 790019 number of values. So the reason for that is, if you see here, this image comprises of 197505 pixels. We multiply the height and width of the image to get the total number of pixels available. Now for each pixel, as I said earlier, there are 4 values associated with it: RGB and the alpha value. So if you multiply the total number of pixels by 4, then you get 790020. These are the number of indexes that would be present in this particular segmentation map object. Basically, pixel wise color information is present here. Now, how do we render this output? So basically, we take the prediction object and then divide it into its individual attributes, and then we use the segmentation map, and then pass to the image data. We create a new image data object, pass the segmentation map width and the height to its constructor, so that the image data, so we are able to get an image data object out of it. This image data object can be later passed to the canvas.context.putImageData to draw it on the canvas and then finally display it on the screen. Okay, so basically this particular, all these indexes, everything, this refers to, if you go and read what the image data object is, there would be a data attribute within the image data object, and that data object basically would contain pixel wise color information for any image that you have. So the same thing is mapped here, and that's why we are able to use the segmentation map to create an image data in the first place, and then use that image data to display it on a canvas using context.putImageData. And this would be the sample output for a given image Here it has identified all the person, and then it identifies this as the background, and here there is a small blue color that is nothing but it thinks there is a boat at this point somewhere. This is how it identifies it. Okay. In the next video, we'll take a look at the source code for a sample app, and then we will also walk through the entire code and understand how it is basically implemented. Thanks for watching. Look out for the next video. Thank you.